Here's another balanced tree. This one's on the edge of Waimea Canyon on Kauai along the cliff trail. In this screencast, we're going to look at insertion and deletion. And I should mention, if I didn't make it clear in the last one, the reason we're interested in balanced trees is because the operations of search, insertion, and deletion with binary search trees can degenerate to order of n if you get quote-unquote bad data, like insertion of data in sorted order, so it degenerates to a linked list. So balanced trees are very important for efficient implementations of dictionaries. So let's take a look at insertion and deletion. Insertion into a 2-4 tree is similar to that of the binary search tree in one respect. You search for its expected location, and then when you don't find it, you put it there, although here what we mean by there is a little bit different. Rather than putting it at the leaf node we expected to find it at, or that's not there, we put it in the parent of the leaf node reached by searching for it. So let's take a look at an example here. Let's say we want to insert the key 9. So we go into the root node and you do a linear scan across the keys to find, comparing to each of the keys in the root node. For example, here it's less than 10, so that means we go left of the 10. So we look down here, it's greater than a 2, so keep going, greater than 8, keep going. We're out of keys, so go right down here, so then we go right down here, and we look here and it's empty, so we know that it's not in the tree and we can insert it. Although with a binary search tree we would insert it here, but we don't actually do that with these trees. We insert it here and then we add an extra empty child, so now there's 4 of these here. So this is a 4 node. It's got 3 keys and 4 children. So that's the basic idea. Search just like you did with a binary search tree, but with these multiple keys at a node. Find the empty leaf node where you expected it, and then insert it as a key in the non-empty internal node that's the parent of that empty leaf node. This insertion procedure preserves depth because we always put keys into a node that's already existing and we don't extend the depth of the tree anymore, at least in what I've told you so far. But the problem is it may cause overflow. So a node may become a 5 node. So the example here is inserting 30. And we check it's greater than 10, greater than 15, greater than 24. We go down here. It's greater than 27, less than 32, so we expected it here. So we're going to insert it right here and make a new leaf node, and that's what's been done right here. We've got the new 30 inserted and a new leaf node. But now this is a 5 node. It's got 4 keys and 5 children. And that violates the property of the 2-4 trees that they have to be 2, 3, or 4 nodes. So we're going to handle that with a split operation. So overflow is handled with a split operation. We'll see this here with a tree that's a little bit simpler than the one we were just looking at, but it has the situation where a key has been inserted into a node, making it into a 5 node. So a 5 node will have 4 keys, and so that's split into a 3 node which has 2 keys and a 2 node which has 1 key. So you notice there's 1 extra key we have to do something with. That key goes up to the parent node. So we'll get back to that one in a bit because that may lead to overflow. But let's just look at this basic operation here first. We have a 5 node that was created here, so we're going to, and it could have been created by the 30 insertion here. Right now 32 is highlighted in red because that's the one that's going to be bumped up to the parent, not because that's the one that was inserted. It doesn't matter which of these nodes, which of these keys was inserted. We're just going to take the first 2 and split them off to be their own separate node. The last one, split it off to be its separate node, and promote that 3rd key up to the parent node. So that solves the problem of this node has too many elements in it, and it solves it without increasing the depth of the tree. We haven't gone down and added any leaf nodes down below. But of course this parent node here could overflow. And that's actually the example, if we can just go back here really quickly, that we saw here, that if this node here is split and then the it would have been that 32 went up in that example, and then so the 32 would have been written up here, and then we'd have another 5 node, because remember these two nodes would have been split into the 2730 node and the 35 node. So again, we got 4 keys, 1, 2, 3, 4, 5 nodes, and so we would repeat the propagation upwards to its parent, hopefully until it finds a home. But if you don't find a home, that's when the tree grows. Notice that only after you've propagated things up from the leaves and you haven't been able to find a place to put it is when you would actually say, okay, I'm going to put a new node up here. So I'm not really discussing the details of how you would do that and what the code looks like here, because this representation we're looking at now isn't actually implemented. This is a conceptual representation. And again, it's useful. It's a useful representation because it guarantees that the tree is balanced, that it's packing in as many nodes as it can. But it's kind of hard to implement something with 2, 3, or 1, 2, or 3 keys, 2, 3, or 4 children. So to give away the punchline on the next screencast, these will be represented as binary trees using red-black trees, and the operations will actually be on the binary trees. But let's continue to reason in terms of this conceptual representation. First, a quick note here that the other reading I gave you, Sedgwick's reading, and some other texts will do the splitting of the nodes on the way down while they're searching for the position. So if it sees in their approach, if they see a 4 node, that would be one of these things here. While they're searching for a position, it'll just go ahead and split it. But that tends to make the tree grow a little bit faster. It just saves the trouble of having to propagate things back up. So it makes the insertion faster, but it also splits nodes more than they necessarily have to be. But the Goodrich and Thomasia text, out of which I got these figures, and the Cormen et al. Text do what I've just described. They propagate the splits upward only as needed. But what about the complexity? Well, we already established that a tree with n items has theta of log n height. So the algorithm first searches for the insertion location. That requires going down to the leaf, because we have to go to the leaf. We're going to say it's theta log n. The insertion is theta of 1 time, but then there's the overflow. Now each split is constant time to do the split, but we might propagate upwards big O of n of log n times. Big O rather than theta, because we don't necessarily go all the way up the tree. We might stop part way up and find a place to put the key we're propagating up. So the larger term here is the theta of log n, because the big O of log n includes cases that might be faster. So conclusion, insertion is theta of log n. And that's the important thing. This is always the case, even in worst case data, unlike the binary search trees, or unlike hash tables with chaining where you get one long chain off of something. These can make a log n guarantee in all cases. Okay, what about deletion? You may remember with the binary search trees, when you want to delete a node that's internal to the tree, like say you want to delete 24, which is up here, in the binary search tree, we would go find its successor, and we would move its successor up to the position of the node to be deleted after putting the successor's children in a reasonable place. And you may recall with binary search trees there was only a right child. There's never a left child of a successor, and so you just move the right child up to the successor's position, and the successor goes up to the node being deleted. But here we have these nodes with multiple keys, and we have the fact that the leaves are always these empty things. But we still have this idea that we replace the key with the successor. So here we've taken the 27 out of here, and we've put it up here, and we've reduced the size of the node that the 27 was in. Instead of a 4 node, 3 keys, 4 children, we now have a 3 node, 2 keys, 3 children. So that all works pretty well. And that means that we have a way of dealing with deleting keys that are in these higher level nodes that reduces it to the problem of deleting keys in the a node that has leaf children. So now for any complications we only need to consider this case where we're deleting from a node with leaf children. So as you might guess, deletion from a node, we've dealt with the internal node case. We're just deleting we're considering deletion from the leaves now, but that may cause underflow. And here's an example. There was some key here that we deleted, whether it was because we were deleting something up here and it was the successor and we had to move it up, or this key directly was the one we wanted to delete. Suddenly a node that had one key now has 0 keys. It's called a one node because it has one child. So that's not allowed either. So there's 2 cases for dealing with this. The first case is where we have a sibling that's a 2 node, like this case right here. And the simple solution is to do a fusion where you merge the 2 nodes. So as you can see, we just took these 2 nodes here and they become one node here. But in order to do that, we have to give this node another key, because there's now 3 children and you can't separate 3 children with 1 key. You have to have 2 keys to separate them. So we pull the entry that falls between these 2 nodes, because there may be multiple entries up here. We pull that one down into here, and so the 14 comes into here. So now we have successfully dealt with this underflow without changing the height of the tree, which is crucial with these things. Of course, there is the possibility that underflow propagates up to the parent. Suppose that only had 1 key in it and we pulled it down. So it may propagate to the parent, but that's at most, it's bounded above by log n adjustments up the tree, where each adjustment is constant time. So that part of deletion you can see is going to be log n to potentially log n to get down to the, always log n to get down to the successor, to put it up there. We always propagate the deletion down to the leaf node, and then potentially log n to propagate up underflow back up to the top. And of course you can imagine underflow could eventually reach a root node that has only 1 key, and in that case you would end up removing that root node level. But again, we won't talk about how to do this in this 2-4 representation, because it will actually be done in the red-black tree representation. But we have one more case to deal with. So case 2, of course, is where a sibling is a 3 node or a 4 node, where it's got more than 1 key in it. And so rather than just merging, we can do what's called a transfer operation. We can keep the same number of nodes, but essentially we're going to rotate keys around like this. So the 8 is going to go up to there, and the 9 is going to go down to here. So we shuffle keys around, and so this one, which was a 3 node, now becomes a 2 node, and we know that that's safe, that's okay. And this, which was a 1 node, now becomes a 2 node. So transfer eliminates underflow without any need for propagation up the tree, because notice that we did not change the number of keys in this node. This node stayed legal because it's still got a key left, and this node became legal. So there's no climbing up the tree. So to summarize, of course, the deletion is going to require theta of log n to find the node to delete, including finding the successor that replaces it. And then underflow might be handled in the first case with up to big O of log n fusions, and one transfer, because one transfer always stops the underflow. They each take theta of 1 time, so it's dominated by this thing here, so deletion is theta of log n. So again, we have a guarantee of log n behavior with these balanced trees, which is what makes them worthwhile. So we've got that guarantee for search, insertion, and deletion, the major operations that you do with these dictionary representations, and that cause problems with the binary search trees. So that concludes our presentation of insertion and deletion in 2-4 trees, which are balanced and have good logarithmic behavior. But now the question is, how do we implement these things? And this is where we really get into the thick mess of branches as we get into red-black trees.